Hello, welcome. Multimodal image text classification. Understand the top deep learning image and text classification models CMA Clip, CoCa, MMBT, EmbraceNet as used in image text classification, for example, in case of e-commerce. So, hello, welcome. This is another video. This one will be rather quick about classification, for example, of products on e-commerce website. And you can subscribe on YouTube. You can subscribe on by mail for my newsletter. I'm also on Twitter, like here. I have the links at the end of the articles on the homepage. All right, so I write posts on machine learning and software. So today, this one is about image and text classification. So input to the models that we train and then use to predict with is image and text pairs. So basically, it's multi-modal system, and output is a class, or sometimes it could be embedding vector, which can be used for similarity or multiple purposes. And it is this has use cases, for example, in classification of products into the product taxonomies. I have one page about this. For example, in Pinterest, they actually are building product classification. This is important in product aggregators, so you need to have the added value of aggregator is that the products are presented in very nice overview. And in, for example, in case of Pinterest, this is instead the case that they want their advertisers to be able to select where they on which pins they would like to advertise. And in very common taxonomy to which we can classify products is this Google product taxonomy, and you can like play with this interactive viewer of that. Anyways, let's go back to the classification. And at the same time, multimodal models are important in other domains now. So there are new models, for example, like CoCa, which uses both, and by using both, they can then outperform on even just a single modality. So there's doesn't seem to be so much trade-off. It can like training on data sets which contain both image and text can actually improve performance on the image data sets as well. So for example, this CoCa model has at least this year state of the art on ImageNet dataset. Okay, here's an image example. So how this works, right? So we have as an input we have this image of some product, for example jeans. We have some description of the product, and then we use both of the inputs to feed them into some specific parts of the model, and then we aggregate them in some fashion, and then we predict the classification. Before going into the classification, let's first look at the very famous multimodal model called Clip, which was presented in this paper January 2021, that encodes image and text separately, but such that their embeddings, the vectors, the output of those models, are very close together for related text and image. So this model was trained on proprietary web image text, but there are open source models that already exist separately, for example using Lion dataset. I think I will add the link here. And so the training of this model using contrastive learning. Basically we maximize similarity between those related text and images and minimize similarity between those unrelated. So specifically it works as follows. So we have some textual input, image output, we encode them, we use separate networks to encode them, get vectors, get embeddings from those, And then we make sure that since we encode multiple images, multiple texts, then once we do the dot product between all combinations, that corresponding image and text has the highest similarity, very close to 1. You know, there's this normalized dot product called cosine similarity. So we want to have on the diagonal where there is this relatedness to have value 1 and off diagonal 0. So, and in this way, Clip can produce very nice embeddings which are useful for other purposes as well. How? What is the architecture of Clip exactly? So, Clip can have multiple architectures, but the most common, like this overall, it's not 100% specified, but the very good performing variants of this architecture are in fact transformer encoders. So you can have a visual encoder, image transformer encoder. You can read more about transformers in here, and there's can click on this link, and I have notes on transformers as well on the web page. So you have this visual encoder, text encoder. Visual encoder is this famous paper here. Then we have this text encoder, which is GPT-2, or some other transformer models. And then to get actually fixed length embeddings, right? We need at the end, if there is very long text but very small image, we still want the same size of the vector. We need to have same vectors. So there's some kind of pooling applied, and in case of text in the original paper, they just used embedding extracted from end of sequence tokens, but there are other ways this pooling can be done at the last layer. And for vision encoder, similarly, you can have a classification token from which you can extract the final embedding. But important thing to note here that while we can do the pooling at the end, it's still possible to extract, if both are transformers, still possible to extract full sequence. Okay, what are the applications of this model? So for example, DALL-E 1 uses this. I have a web page on that. DALL-E 1 uses it for generating images. That's that model for image generation, where we first encode into this we use variational autoencoder, which is however discrete. So we encode and quantize into some dictionary, and then we use transformer to predict next token and consecutively generate the image autoregressively. There, the clip model that I'm talking about now is used for re-ranking, so it's just a final judge on the output. In DALL-E 2, the clip used the DALL-E 2 used the clip embeddings directly, and I can show that one. So actually, you use the text encoder, use also the image encoder during the training, and you use those to train this translation from text embedding into the image embedding. They are not absolutely the same, so it's useful to do this conversion, and that's where we use this clip. And also at the end, of course, we have to have something that generates the images. So there's a diffusion decoder which uses the image embedding as input. All right. Okay, so let's go back. And but the clip can be used for other very simple use cases. For example, for zero-shot image classification. So for each class, you can create a text describing a class, and then you can take the image and you can embed the image, get a vector, and then compare which the class text is the most similar in the vector space, and then basically you decide using that where the image should be classified. And as well, you can use this for supervised image text classification. Either you can use you can just sum up the embeddings from the two modalities. So that's also a possibility. Or you can train an MLP on top, or other things. Important is that you have these interesting embeddings that will help you to do the classification. Alright, so this was a clip model which was used in those other applications. Here we have one big application for image text classification. So this was a paper from Amazon where they designed an architecture which is most useful for multitask classification of products. For example, in case of fashion, we can be detecting multiple things about the products from the same embeddings. How this works I will describe soon, but we have some clip backbone, transformer, and we have some specialized modal device attention which can then help us to do very well on multiple tasks at the same time. Basically, the principle is that we use this fusing of the information from multiple sources, and but to do this task specifically that we can ignore input that may not be important. And what's important about this paper is that it beats sort of these two other main approaches by combining them. That describe that there are these two-stream approaches and one-stream approaches. The two-stream approaches that mean that those are that they don't fuse the information from the modalities for a long time, and then it's only aggregated at the end. That, for example, in case of a clip, if we have just very shallow network at the end, we can consider it two-stream. Or this MMBT model, if we use ResNet, we can say that large part of there is very little interaction with detailed parts of the image, because we don't work with the specific tokens that describe local information. We use only aggregated information from the ResNet of the convolutional network. Yeah. Okay, and there's this one stream approach where mostly they describe that those are often models that are very complicated, that they align some, they use some task where they align image tokens with text tokens, which seems overly complex. Okay, what is the architecture of CMA Clip specifically? Okay, so as I described, you can use Clip as a backbone to encode image and text, but you don't have to use just the pooled fixed length result. Instead, you can concatenate the two sequences that come out of the transformers, if you use transformers for both image and text. And since you get a sequence, you can feed this sequence into a transformer, and then at the end you can still pull out a fixed length vector from those classification token positions, and then you can treat those as if they were really just about one of them about image and one of them just about text. But it's not longer any true, because the transformer actually mixes significantly the information between. Still, it helps to think about it in this way. And yes, and what they add here in the CMA clip is this modal device attention, which is basically just weighting. So it basically uses per task, they have some kind of projection vector which describe what we are interested about in the embedding, and they do multiplication separately for image and text class token embedding. And As a result, they get some projection into this vector, and they use it as a weight. So this cosine simulator is used as a weight, and basically then this weight tells us, okay, is information in this modality important for the classification for the specific task or not, because this architecture is trained on multiple tasks, as mentioned. For example, detecting color, detecting the cut, and detecting maybe this sleeve length, short sleeve, long sleeve. And so this removing of the irrelevant information helps, and this seems to be something general, but I don't have some general behavior of neural networks. I don't have the sources here, but I saw it on other places as well. So Cma Clip was actually tested on multiple data sets. I have listed these three: Food 101, Fashion Gen, and their own Amazon proprietary dataset for color, pattern, and style. They have okay. So all of those are image text datasets, obviously, and they include involve classification. The result, overall, Cma Clip is performing slightly better than MMBT. MMBT has very similar architecture. It doesn't have this multitask specialty. It wasn't constructed with idea of image transformers, but it has the architecture is very similar. So, and the Cma Clip is not performing that much better in terms of accuracy on Food 101. In the comparison, we don't have a parameter count, so it's possible that in some cases the Cma Clip may be just much bigger model, so of course it's going to perform better. Okay, and let's look into the detail. So Cma Clip outperforms KaleidoBERT and ImageBERT. I think those are, if I remember, those are more complicated models that actually do this aligning of image and text, or they try to detect something in the images, something specific. And unfortunately, on Fashion Gen, which is this fashion dataset, there's no benchmark for MMBT, which is actually this, I think, second best or clip. Okay, on Food 101, the Cma Clip outperforms MMBT, but by just a small margin. Yeah, by just 1%. So MMBT is 92, Cma Clip is 93. It seems that this task is rather close to saturated. There will still be some noise in the dataset, and so we are very close to this dataset not being useful. That's my speculation. I haven't read about something rigorous about it, but it just seems like it. And yes, and I think here the MMBT performs very well, and it's just very similar architectures. So yeah, maybe just the Cma Clip, maybe the clip has better embeddings, maybe Cma Clip is bigger. Yes, what's interesting here that on this task, pure text model is better than visual transform. Okay, Cma Clip on proprietary MRWPA dataset of Amazon, and here they just compare with Clip, and of course they outperform since they are much bigger models. So I think one important thing here is that I think that actually it will be visible more in the ablation results. Alright, so image text alignment. So this is something interesting that you may like. It's interesting to look at that. Actually, the model seems to learn some alignment between the text. That if you ask about a token in the text, to what it attends to in the image, you will find that oftentimes there is some alignment that you can basically get an answer where the lobster is on the image. Yeah, so if you provide the text and image separately, and then you look at the where is this lobster token attending to, because you have both token sequences are on the input, then in this transformer you can have a look where are which tokens related via attention, and you can find apparently using attention map on one of the layers. I'm not sure is it all layers or just one layer, at least it's one layer, one head, I guess. You can find this interesting ability to actually detect where is the token of the text located on the image. Okay, Cma Clip ablation results. So this is interesting. This is where they remove the modality-wise attention, and this is where we can see that modality-wise attention is going to help the most on the tasks where there is big one of the modalities is simply not useful at all. For example, in case of style, that's something that's often not mentioned at all in the text, and so that's where the modality-wise attention is going to help in context of multitask learning. In single task learning, this wouldn't matter that much because the model would just learn to ignore the modality using other weights. But if you are using multitask learning, the end result embedding needs to be very universal, and maybe there you can learn explicitly to ignore some parts. So this is what happens here. We can see it that on style there is the biggest difference relatively. Then, for example, in case of color, for example, is very often mentioned in the text in the fashion context, and so this is something I would expect that the modality-wise attention is not going to be so useful in this case. Okay, I'm going to mention a couple other models. So this was a Cma Clip. I'm going to mention a couple others. So there's this model CoCa, which the idea there is that you learn not only to align the text and image embeddings, but instead you also learn to reconstruct the text at the same time. And this apparently helps a lot. It combines contrastive loss with the caption task, and it helps so much that the CoCa then outperforms on ImageNet and becomes state of the art. And actually, it's so well-rounded model that it actually gains state of the art on those many other datasets. Yeah, I want to mention that image text is just about images, so there's no text involved, and still CoCa this bimodal bimodality model still won. Okay, there is also this MMBT model I keep talking about. It's very similar architecture to Cma Clip, so you can see that on the image we have ResNet embedding here, which is then projected in multiple tokens, and this is concatenated to the text tokens, and then we go through the classical transformer and get the and then perform train classification on that. So you can see that it's very similar, except the backbone is different. So we use ResNet and linear projection instead of actual visual transformer, which is much more natural, and we don't have a modality-wise attention. Also, honorable mention, EmbraceNet, it actually won some competitions on combining multimodal inputs. It's probably a very nice model, probably very useful for smaller data as well, and it is fairly simple. It basically does it has multiple heads which perform encoding of the different modalities, and then the combination is summation. But here's the trick. The summation is sort of like it can be weighted summation, but important here is that there is sort of like feature dropout that is performed here, which helps a lot with this is like the weighted summation with sort of feature dropout and normalization, which improves the results by dropping certain features, and yeah, it's just improves the results. And so here's the summation, and then after the summation of the different modalities with this feature dropout, we perform terminal network and get a final decision, final classification. So this was video on images classification. You can connect. You can to me. You can subscribe. You can ask me some question. You can follow me on Twitter, YouTube, or other. Facebook, on other platforms, and I hope you enjoy it. I have other posts on my website, so you can have a look. Okay, thank you very much. I hope you got the gist, the juice of the paper, and see you in future. Bye. Subscribe.